All right, hello and welcome to your review video for test number 7 for this unit. We are going to start by doing a little bit of a review about limits. So hopefully you've noticed for questions 1 through 5 it says find each limit. Questions 1 and 2 are talking about limits at the ends of the graph, so infinity and negative infinity respectively. And then questions 3 and 4 are talking about the limits at a point. So how do we evaluate at a specific moment on a graph? And then question 5 is asking for some limits from the left, from the right, and overall, again, at a point because we're going to a specific x value. So when we start with limits at infinity, as I mentioned, you're talking about what's happening at the end of your graph. So by the time you're out at infinity, things like -4 and -16 don't really make an impact. So we look at this and we say that we are comparing x to the first and x to the second, and x to the second is going to get larger a lot faster than x to the first, especially by the time you are out at infinitely large values, in which case the bottom function is the one that is going to impact our limit, and things that are bottom heavy or dividing by a bigger number on the bottom are going to approach 0. For question 2, the limit as x goes to negative infinity. So again, by the time you're at negative infinity, things like 6x and 8 don't really do much, and really you're comparing x to the second and x to the second. So these are racing to negative infinity, and if you think about x to the second and x to the second racing, well, they're racing at the same speed, so to speak, but this one's going 4 times that speed and this one's going 20 times that speed. So when things are even in heaviness or equal in degree, we look at those leading coefficients, which simplifies to a 1/5. The last situation would have been top heavy, right, where the top one is racing faster, in which case you would do some division to figure out the end behavior of your resulting slant asymptote. All right, so the limit as x goes to 4. Now this one's a little bit different because we're talking about at a specific value of 4. So your first method for evaluating a limit is to just plug in the number. So if I plug in the number, I end up with 0/0, which in my head means I need to keep going. And some ways that you can keep going are factoring, conjugate, denominators, using algebra of some sort. And so for this one, I can see that the bottom factors into a difference of squares. So now x minus 4 cancels out, and I have a brand new limit problem of the limit as x goes to 4 of 1/x plus 4. So now that I've gotten rid of this problem, which was a hole, if you think about that from your rationals unit, now I'm going to try again, and I'm going to plug in 4 to this expression. 1/4 plus 4 gives me 1/8. Same thing here, the limit as x goes to 9. I'm going to start by plugging in, right? Substitution is your first method. And I end up with 0/0, which means I need to keep going. So for this one, because I have a square root, I'm going to keep going by multiplying by its conjugate. So square root of x minus 3 over x minus 9, and I'm going to multiply by the square root of x plus 3. If I do that on the top, I have to do that on the bottom. And now you want to be careful because you do want to distribute on the top, right? First, outside, inside, last, if that helps you remember. So I'm going to get x plus 3 root x minus 3 root x and then minus 9 over. The bottom you do not want to distribute because ideally something is going to cancel out to get rid of that problem of 0/0. And so if you multiply it all together, it's harder to see that this x minus 9 and this x minus 9 are going to cancel. So now I have a brand new limit problem. The limit as x goes to 9, 1 over the square root of x plus 3. First method to evaluate a limit at a point is substitution. So I'm going to plug in 9 and I end up with 1/6. Okay, so again, the reason you pick a conjugate is you are forcing a difference of squares so that things come out nicely and then something will cancel top to bottom. The other thing you could do, you guys were taught how to factor a difference of perfect squares. Well, you can just leave the top as the square root of x minus 3, and then the bottom does factor out into plus and minus. This will be 3 and 3, but instead of x, it's going to be the square root of x and the square root of x, and now these things cancel, and I still get my same limit problem from here. But multiplying by a conjugate will do the same thing. It forces that difference of squares to appear. All right, so limit from a graph. We're going to start with 0. So it helps when you're thinking about left and right let me get this situated. We're going to block off part of our graph. So for instance, if I want to look at 0 from the left, I don't care about this right side of my graph at all. And what I want to do is I want to follow this trail and figure out as x goes to 0, what is my y value pointing to? And my y value is pointing to 0. Then if I want to look as the limit as x goes to 2 from the right, I can cover up this whole part. Those little arrows are still there. And now I want to talk about as x goes to 0, what is my y doing from the right? Well, that's going to 2. And because 0 and 2 are not equal, we would say the overall limit does not exist. For the next one, so that across the top should have been 0, 2 does not exist, if you see that on your answer key. The next one's the limit as x goes to 2 from the left. So I'm going to cover up everything from the right. And I'm going to trace as x goes to 2, what are my y's doing? My y's are going to -2. If I move this, as my x goes to 2, what are my y's doing? They're going to 0. And because the left side does not equal the right side, the overall limit does not exist. You can see that you have a nice jump in your graph, just like you did at 0. And then the last set is talking about what's going on at 4. So 4 from the left, here's going to 4. My y value is pointing to 4. From the right, going to 4, my y value is also pointing to 4. So you'll notice that my roads are leading to the same place, which means the overall limit is 4. Now it doesn't matter that there's a hole there, because the roads are leading to the same place, and we don't care about what's going on at that value, we care about what's going on near that value or as we approach that value. All right, now we're going to jump into Unit 10 a little bit, rewriting the equation in exponential form. So you have a logarithm. The inverse of a logarithm is an exponential. So I would write this as an exponential with a base of x because my logarithm had a base of x. These then cancel. Y is equal to x to the -19th. You also can do, one of my students calls it a recycle method. X to the -19th equals y. So we should be looking at answer choice A. This one, rewrite in logarithmic form. While I have an exponential, the inverse of an exponential is to use a logarithm. So I'm going to choose log base b because my exponential was a base of b. What you do to one side, we got to do to the other. So now on this side, these are going to cancel out, and I'm left with b to the 5/3. Oh, sorry, and the b cancels out. I was like, what is happening here? We're left with just the 5/3. I was going to get right back to where we started. Equals log base b of a, which should be looking at answer choice B. All right, solve each equation. Remember, there's a lot of different ways. The first way to solve an exponential is to try to rewrite with the same base. If that doesn't work for you, then you can try to use a logarithm with the base of the exponential if you have your fancy calculator. Or you can always use common log, which is base 10, or natural log, which is base e. But here, I'm going to look at this, and I think both of these things can be written with the same base of 6. So this really is 6 to the 2nd to the 3n, and 216 is 6 to the 3rd. So when I have a power to a power with exponentials, I'm going to end up multiplying. So this is 6 to the 6n equals 6 to the 3rd. Now that I have the same base, I can just say that 6n is equal to 3, which means that n is equal to 1/2. This one, 125 to the 2v equals 1/5. Again, methods for solving an exponential, you can rewrite in the same base. You can use a log of the base that you see if you have your fancy calculator, or you can use a common log or a natural log. Well, looking at this, 125 and 1/5, I'm thinking I can write that with a base 5. So 125 itself is 5 to the 3rd, and that will then be to the 2v. And 1/5 is the same thing as 5 to the 1st, but it's been flipped and made to be in the denominator, so 5 to the -1. So just like on this last one, when you have a power raised to a power, you're going to multiply. So this is 5 to the 6v equals 5 to the -1. Now that my bases are the same, I can say that 6v is equal to -1, which means that v is equal to -1/6. All right, so that was one way of solving exponentials when we had a perfect exponential expression equal to a value. Here we're just going to have an extra step before we can get to that exponential part. So I want to isolate the exponential. which means I need to subtract this too. So I've got 10 to the 3b equals 57. I don't think there's going to be a way to rewrite 57 in a base of 10 nicely, so I'm going to choose to take the log of both sides. So log 10 of 10 is going to cancel out, and I get 3b equals log of 57. To get the b by itself, I'm going to have log of 57 divided by 3, which is, again, answer choice A. This one, here's my exponential expression. So the thing I need to get rid of is this 3. So I'm going to start by saying, I don't really have a lot of room, but e to the n plus 10 is going to equal to 37 thirds. Now there's not really a way to get e written, 37 thirds written with base e. So I'm going to choose a logarithm, and I'm going to pick the natural log because that has a base of e. So these are going to cancel. I'm going to get n plus 10 equals the natural log of 37 thirds. To get n by itself, I'm going to subtract 10. So we're looking at answer choice A. So again, method there. Tried to rewrite with the same base, wasn't going to be possible, so I choose a logarithm of both sides. All right, so now we're solving logarithmic equations. To undo a logarithm, you're going to use an exponential. Well, both of these have log base 10. So yes, officially you could rewrite this as 10 to the log of 4x plus 2, because I'm using an exponential to undo that logarithm. And these are going to cancel. But the other way is to say if I'm taking the log of this, and it's equal to the log of that, with the same base, well, what must be true about this and that? The two things inside, or the inputs to the logarithmic equation, must be equal, which is what we're about to get to right here, is that 4x plus 2 is equal to 5x minus 1. So this is going to be 3 is equal to x, answer choice A. Likewise, here I've got natural log of this is equal to the natural log of that. So the shortcut is to set this equal to that. But you also could say I want to undo a natural log, and I undo a natural log using an exponential with a base of e. Now these cancel, and I'm still right to here. I'm going to add this to the other side. 10 is equal to 2x, which means that x is equal to 5. With both of these, you do want to go back and plug in your number and make sure that they work, because the natural log has a domain restriction in its parent form that your input has to be greater than 0. So if I plug in 5, I would get negative 5 plus 10, which is positive 5. We're all good there. Natural log of 5, good there. This one, if I plug in 3, 4 times 3 is 12 plus 2 is 14. All good. Plug in 3, 5 times 3 is 15 minus 1. We're all good. All right, so these ones are similar. We've got logarithmic expressions in our equation, and we would like to get them to go away. But before I can use the little shortcut that I just had, I have to have a single log equal to a single log. And this was our purpose in that 10.4 video, all about properties of logs. So because this is addition, addition for us is going to turn into some multiplication. So I'm going to have x plus 5, x plus 20, equals log of 34. Now I have a single log of this equals a single log of that. So I would say that x squared plus 25x plus 100 is equal to 34. And you can solve this lovely quadratic. You're going to end up with x equals negative 3 and x equals negative 22. Okay, because we would have x squared plus 25x plus 66 is equal to 0. But when you go through and you test those answers, it is only the negative 3 that works, because when you plug in negative 22, we would get negative 22 plus 5, which is negative 17, and you can't have that as an input for a logarithm. All right, this next one, same thing using properties of logs. So I'm going to get the natural log of x divided by 2 is equal to 2. Now to get my natural log to cancel, I can't just do this and that, because this doesn't have a log with it. So I'm going to need to undo a natural log. Those are going to cancel. X over 2 equals e squared. Multiplied by 2. We're looking at answer choice B. All right, 16 through the rest will be on your second review video.